Okay, this is your review as far as force diagrams and circular motion. The force diagrams are the key to any conceptual or math type problem that you will deal with circular motion. All right, so make sure you make note of the difference between a force diagram and a centripetal force diagram. It's very similar to the difference we had between force diagrams and net force diagrams. Centripetal force is a net force that only occurs when we are moving in circles. Okay? So, first we'll stick to horizontal to start, and then we'll move to vertical situation. So what horizontal means is that the circle is on the surface. All right? Gravity never points in the same or opposite direction of your centripetal force. It's always perpendicular to it. All right? So let's talk about a car on a track or a merry-go-round or anything where the turntable with the quarter. Those would all be examples of horizontal circular motion that have these two particular force diagrams. So the forces we will have, say we're right here on the circle, we will have Fg going down, you'll have Fn going up, and then what was the force that actually kept the quarter on the turntable or the rubber stopper on the turntable or a car on a circular track? Hopefully you are saying force of friction. All right? Now, on your centripetal force diagram, put a dot in the exact same position, and a centripetal force diagram is the easiest one ever to draw. It always points towards the center of the circle. It never points in any other direction, always exactly to the center of the circle. All right? So based on this, if you notice, because FC points to the left, it's based on how our picture is drawn, the horizontal plane. The only other force in the horizontal plane is force of friction. And they both point in the same direction, so they have to be equal to each other. So for situations like this, our force of friction is always going to be equal to our FC. All right? Sometimes in order to solve problems like this, you may have to remember that force of friction is equal to mu times Fn. All right? And in this case, because force of gravity and normal force aren't in line with your centripetal force, it is like being on a flat surface, and Fn is equal to Fg. So these are your hints for these types of problems. Another horizontal circular motion, and I will admit I did make a mistake when we talked about this originally, so pay close attention here, is the rotor ride, or we talked about in class the spin and barf. This is the ride where kind of like from when I was a kid, it looked like a spaceship, and it spins really, really, really fast, and once it gets to a high enough speed, the floor drops out, and you are stuck to the wall. Okay? So say we are here on the wall. Force of gravity, always going to point down. All right? The difference is, though, think about what surface your body is actually on. It's not on the floor anymore. The only surface your body is touching is the wall behind your back. So what that tells you is that your normal force is actually the force pointing towards the center. All right? And then what is the force counteracting force of gravity that is making it so that you aren't sliding down the wall? That should be force of friction. Okay? Your FC will look the exact same. Put the dot exactly where you are. FC always points to the center. So for a rotor ride or a spin and barf or the ride where you get stuck to the wall, your force of normal is equal to your FC. All right? And in this one, you still may have to remember that F of F is equal to mu times Fn, which you could rearrange to solve for normal force. And in this case, force of friction is equal to force of gravity. Okay? So those are some helpful hints for this type of problem. So let's start talking about vertical circular motion. All right? So there are a few different situations. Vertical circular motion could just be that you're going up and down, but you never go upside down, which would be like a car on a hill. There's a couple other situations where you could go upside down, and then that changes things a little bit. So let's talk about circular motion on a hill. So we have top of the hill, bottom of the hill, or the bottom in between two hills, so there's actually still a curve, versus a flat surface. So at the top of the hill, Fg always points down, and Fn points up. If you look at the circle for your Fc, that points down, All right, now in this case, your normal force and your force of gravity are in the same plane as your centripetal force. All right, so those do actually impact the centripetal force. Now, because Fg and Fc both point in the same direction, though Fg has to be the bigger number. So Fc is equal to Fg minus Fn. Okay, now here at the bottom of the hill, force diagram looks the same. Fg points down, Fn points up. Okay, your centripetal force diagram, however, now points towards the center, which is actually in the up direction, which then changes what Fc is equal to. In this case, normal force has to be bigger than Fn minus Fg. Okay? Now, and I'm talking about this because I want to clear up, I actually am admitting another mistake that I made was related to that question 3 in the conceptual ideas and about where the force the car applies to the ground is more. And it's actually not from Fg. But here we have Fg and Fn, and there is no centripetal force. Our F net equals 0. Okay, so in this case, in order for F net to be 0, Fn equals Fg. So, similar to the way we described this problem before, is that in this situation, it's neither the most force or the least force, but I actually had it backwards. What Fg cannot change. Your force of gravity is always the same. So that's actually not what determines the force applied to the ground by the car or a sled or anything like that. It's actually Newton's third law, the reaction to the normal force. Right? Because normal force pushes up on the object, and Newton's third law, that object pushes down on the ground. All right? One way to think about this, because Fg and Fn aren't necessarily third law pairs. Say you are sitting in a wagon on the ground. All right? You have your Fg pointing down towards Earth, and that's the Earth pulling on you, and you pull up on the Earth. But your normal force is actually the wagon pushing up on you. So Newton's third law would be you pushing down on the wagon. All right, in that case, when you push down more, that's when your normal force is bigger. So this is when you would push the most, and this is when you'd push the least. All right, so if you need to kind of refresh yourself on that question, it was number 3 in the questions in chapter 5. So let's talk about vertical circular motion on a string. All right, so this is like when you have a stopwatch on a string and you're sitting there twirling it upside down next to you, you know, like above your head, that sort of thing. Or if you have a ball on a string. So any example like that. And for this one, it is good to sit there and actually talk about different locations on the circle. So we're going to start with the bottom. All right, so at the very, very bottom, we are going to have force of gravity going down. All right, and then if you think about a string, force of tension is going to go up. All right, if you think about it, the string is always going to be right here at the very, very center of the circle. All right, so the string always has to point towards the center, or the force of tension will always point towards the center. Your Fc will always point towards the center. So Fc is going to be equal to your Ft minus Fg, okay, at the down area. If we are dealing with, say, at the very, very top, okay, again, Fg will point down, but so will your force of tension, because force of tension has to point towards the center of the circle, because that's where you're holding on to the string. All right, and then Fc also points to the center of the circle. Now, both of the arrows are in the same direction as Fc, so Fc is equal to Ft plus Fg. Okay, and let's see. If we also talk about, say, at the 3 o'clock position, all right, or the right side. We'll have FG pointing down, all right, and then, but the string still has to point towards the center of the circle because that's where your hand is. So force of tension goes in, and your FC goes in. So in this case, FT is equal to FC. And if you, say, had a question where was the 9 o'clock position, it actually is the exact same thing. FG, T, and FC. All right? So at the 9 o'clock and 3 o'clock positions, FG is what looks like on here, vertical, and FT is horizontal. Since our FC is in the horizontal direction, the only thing that factors into it or needs to be added, summed together to find FC is your tension force. Okay? So if you have circular motion on a string, if you've got tension, you must go upside down. You can't not go upside down because then the tension would be released in the string and that wouldn't work. Okay? Okay, let's talk about vertical circular motion on a surface, but you stay right side up. This is absolutely identical to a car driving on a hill or a car driving on at the bottom of a hill. So at the very bottom, we have FG and Fn, and our FC is going to point towards the center of the circle. So FC is equal to Fn minus FG. Alright, now we need to talk about the top of the Ferris wheel. We would have FG pointing down. You're in a car, so your normal force still points up, and FC would point down. So we have FC equals FG minus Fn. So exactly like the car at the top of the hill and at the bottom of the hill. All right. So last vertical situation we're going to talk about is, say you're on a roller coaster or something where you're in a car and you end up going upside down. So you're in an airplane and go in a circle upside down. So we'll start down at the bottom at, say, the 6 o'clock position. FG points down. Since you're in a car, you have a surface, you have a normal force, and FC points up. So down here, FC is equal to Fn minus FG. Let's talk about the top. Here, FG still points down, but if you think about the fact that it's an upside-down roller coaster, so your normal force, your surface will be underneath you, so your normal force points down, and FC points down. So FC is equal to FG plus Fn, because they both point in the same direction as FC. Now, last situation, if you are on, say, in the loop-de-loop at the 3 o'clock position, we'll have FG pointing this way, but your Fn pointing that way in the same direction as your FC, so FC equals Fn. And looks just about the exact same way on the other side. Got FG, Fn, and FC. So this is almost identical to the something on a string with tension, except instead of having tension, you have normal force. All right, so watch these over, review these force diagrams, and understanding the logic on how to create them is key to being able to do any of the circular motion questions. So fill out the online form as well.